Hello, everyone. Um, Today we are going to continue with the problems we're solving on. I'm going to focus a little bit on homework 2 and homework 3, a little bit about the homework you handed in, and a little bit about the homework you're supposed to solve this week. So before starting, is there any question? Okay, if no, let's start. So I would like to review the previous homework. There are a few interesting things to mention there. So let's just do a fast review about homework 1. Sorry, homework 2. So if you look at the first question which you solved, the first question was this: if A is an element in a field and V is a vector inside a vector space, V, and if we have A, V is equal to 0, then prove either A is 0 or V is 0. Now, it's interesting because there are a few different points which are important here. One is that this might look like trivial, but when we are proving things, we're assuming nothing is trivial. And for every proof we want to use really the axioms we have, the definitions we have, and the theorems we have already proven, right? So here I would write down the proof very fast because I know you kind of know it because you already did this question. So when we say AV equals 0, first of all, the 0 on the right-hand side is a 0 in the vector space, not 0 in the field. Here in the question, if A is 0, it's 0 of the field. If V is 0, it's 0 of the vector space, right? How do we prove that? At each step, we should say what is the kind of theorem or the axiom we are using. So the first thing is that if A is in the field, either A is 0 of the field, which then it's done, A is 0, or A is not 0 of the field. If A is not 0 of the field, one of the assumptions, one of the things we know about a field is that there exists an inverse, right? Therefore, there exists a inverse in the field. So when AV is equal to 0, we can multiply everything by A inverse. So we would get A inverse times AV. And on the right side, we have A inverse times the vector 0. Okay, so on the right-hand side, this thing, A inverse times 0, this 0 is the 0 of the vector space. We want to say this thing is equal to 0 of the vector space. Why can we say that? Is it part of the definition of vector space, or is it a theorem? Is it always correct or not? Okay. Does anyone know the answer? Is it part of the definition of vector space? Or it's something we should prove?
I don't think it's part of the definition.
Okay, so if it's not part of the definition, we should prove that, well, here we have A inverse, but more generally, we probably want to prove for anything in the field, if we multiply that by the vector 0, we would get 0 as a vector. Why is that? So I should prove that first. So that would be a lemma. That's something I should prove. So there are two possibilities. One is that our vector space has only one element, just one element, and that's 0, nothing more. right? That's a vector space. Do you agree? A vector space with just one element, and that's 0. Or there exists a vector v inside our vector space, which this vector is not 0. Let me use another notation. There exists a vector u inside our vector space such that this is not 0. Do you agree? I mean, there are two cases. Either the whole vector space is just 0, just 1 point, the whole set of vectors is just 1 point, or there is other elements but 0. Let's choose one of those non-zero elements u. In the first case, it's kind of trivial that for any element in the field, b times the vector 0 should be 0. In the first case, it holds. Why is that? Can anyone tell me why in the first case, where the vector space itself is just 1 point, this equation is correct? B times 0 is 0.
It's because vector spaces are closed under scalar multiplication. And so the only element in V that B dot 0 could be is 0.
Exactly. Yeah, that is correct. So that's correct. So why is that true? So the way to say it is that we know any element of the field times a vector is another vector. So these things should be in the vector space. But our vector space is nothing but 0. So the only element it has is 0. So it has to be 0. Now, in the second case, where our vector space has non-trivial elements, or things but 0, what we can do, we can say 0 in the vector space is equal to u minus u, right? And then we can multiply both sides by that. And bu minus bu is 0. Anyway, this is kind of trivial. It's just explaining more than I should. But anyway, this is 0. The right-hand side is 0. Therefore, A inverse times AV is 0. Now, the thing I want to do is I want to first compute the multiplication of these two. So the second step you should mention is that this is equal to A inverse A times V. So we want to say, maybe I should write it here. We want to say A inverse AV is equal to A inverse A and then times V. What property we are using? What is the part of the definition that we are using here? Does anyone remember what was the name of this property?
Associativity?
Not exactly. Okay, that's a very good point. You're kind of correct. When we can change the order of multiplication, looks like associativity. But the point is that associativity is for example, product of elements in the field. For example, if in the field I have A, B, C, and where all three of them are in the field, this is called associativity. But here it's different. A inverse and A are in the field, where V is a vector, it's in the vector space. So this thing is not, this is not called, it looks like associativity, you're right, it's just a name. It's called usually the compatibility of like field and vector space products or multiplications. And then we know A inverse A is 1, and 1 of the field times any vector, 1 of the field times any vector V is V. This is, again, another property of the vector space. So the right-hand side is really equal to V. The right-hand side is equal to 0, therefore V is equal to 0. Now, why did I write this more carefully? Well, it doesn't seem very complicated. Why did I explain it carefully? Let's see. The reason is that a lot of times in mathematics, when we are working with these abstract objects, there are things which they look true, they seem true, but they're not always true. Okay. So let me explain a little more. Well, we learned about fields, right? Fields are a set of numbers with two operations, addition and multiplication, where they satisfy some properties, right? Now, there are other mathematical structures. One example is something called ring. So we can think about rings. They are very, very similar to fields. So a ring, very similar to a field, is a set with addition and multiplication, just like field, which is a set with addition and multiplication. So what's the difference? All the properties of the field, whatever we know about a field, ring also has that property. There are only two properties which a ring does not have. So all properties of the field also true in the case of rings. There are only two things which are true for fields, which they are not true for rings. One is that in a field, for any two elements A and B in the field, AB is equal to BA, right? The multiplication is commutative in the field. That's not necessarily true in rings. I mean, it might be correct, but it doesn't have to be. There are rings which AB is not equal to BA. So not necessarily commutative. The other property which a field has is that for any element A in the field, which is not zero, a non-zero element, there exists A inverse, where A times A inverse is equal to the identity or the one of the field. That is not necessarily true about the rings. Some elements might have inverse, multiplicative inverse. Some elements might not have multiplicative inverse. So there might be elements which they don't have multiplicative inverse. So in other words, rings, the definition of the ring is less special than a field. So any field is a ring, any field is a ring, but it's not true that any ring is a field, because you might have a ring which one, it's not commutative, and two, does not have multiplicative inverse. Let me give you an example. Consider Z2. Sometimes people also show it with F2. It's a field which contains only two elements, 0 and 1. Okay, and then everything is kind of clear. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, right? And then 1 times 1 is 1, 1 times 0 is 0, 0 times 0 is 0. Very easy. Everything, first of all, it's commutative, right? 1 times 1 is equal to 1 times 1. 0 times 1 is equal to 1 times 0, right? 0 times 1 is equal to 1 times 0. So it's commutative. And everything has multiplicative, every non-zero element has multiplicative inverse. Well, there's just one non-zero element there, and that's 1. And it has a multiplicative inverse. Its multiplicative inverse is itself, because multiplicative inverse means you should multiply this element by something to get 1. Well, that something is 1 itself. So that's true. So that's a field. So for example, Z2 or F2, both notations they mean the same thing, is a field. What about Z3? Z3 is the set of numbers 0, 1, 2. But here again, everything is kind of mod 3. What do I mean by that? So whenever we add or multiply two numbers together, we should look at what is its remaining after division by 3. For example, 0 plus 1 is 1, 0 plus 2 is 2, obviously. 1 plus 1 is 2. 1 plus 2 is 3. But what is the remainder of 3 if I divide 3 by 3? It's 0. Okay? So whenever we add or multiply two numbers, we would divide the result by 3 and we see what is the remainder. So here 1 plus 2 would be 3. But if I divide 3 by 3, I would say 3 is 1 times 3 and the remainder is 0. So here I can write 0. Okay. What is 2 plus 2? Well, you might say it's 4, but if I divide 4 by 3, I would say 1 times 3 is 3, 4 minus 3 is 1. So I would say the result is 1. Okay, and if we do that, this addition, this set under this addition is closed. So for example, 2 plus 2 is 1, which is another element in this set. And we have the same thing for multiplication. For example, what is 2 times 2? Well, it's 4, but again, rather than 4, we would write 1. And the interesting thing is that this thing here, again, is a field. You can check it has all the properties. For example, I would check if everything has multiplicative inverse. Every non-zero element has multiplicative inverse. Well, what is multiplicative inverse of 1? Well, it's obviously 1 because 1 times 1 is 1. Maybe because I want to say it's a field, I use the cross. What is the multiplicative inverse of 2? What is the number which if I multiply 2 by that number, I would get 1? Well, it's 2 because we saw that. 2 times 2 is 4. If I divide 4 by 3, the remainder is 1. So 2 inverse, the multiplicative inverse of 2 is 2. That's the field. Let's go one step further. Let's look at, so Z2 is a field, Z3 is a field. Let's look at Z4. Is Z4 a field? So what is Z4? Z4 is 0, 1, 2, 3. Now, similar to the things we saw before, the addition and multiplication here are defined mod 4, mod this number. So for example, what is 2 times 3? Well, I should say it's 6, but if I divide 6 by 4, I would see the remainder is 2. So 2 times 3 is 2 here, okay? Now, is it correct? Is it a field? Is it correct that every element has multiplicative inverse? Well, that's correct for 1. 1 times 1 is 1. Good. What about 2? Is there a multiplicative inverse for 2? Is there any number which if I multiply 2 by that number, I would get 1? Let's see. 2 times 1 is 2, and that's not 1. 2 times 2 is 4. The remainder of 4 after division by 4 is 0, and 0 is not 1. 2 times 3 is 6. If I divide that by 4, the remainder would be 2. Again, 2 is not 1. So there is no element which if I multiply 2 by that element, I would get 1. Therefore, 2 does not have multiplicative inverse, right? What about 3? Is there any number which if I multiply 3 by that, I would get 1? Okay, you can answer to that question.
3 times 3 is 1.
Yeah, so 3 times 3 is 9. If I divide 9 by 4, I would get 2 times 4 is 8. The remainder is 1. So 3 has multiplicative inverse. But anyway, this element 2 does not. So Z4 is not a field. Let me tell you something. So Z2 is a field. Yes. Z3 is a field. Yes. Z4 is not. If you look at Z5, it's a good exercise. You can see Z5 is a field. Z6, you can see it is not. Again, 2 does not have any multiplicative inverse there. Z7 is a field. Z8 is not. And if you pay close attention, you would understand ZP is a field if and only if. Can you guess? Looking at these numbers, you might be able to guess.
P is prime.
Yeah, that is correct. So I saw that in the comments too. Yeah, that's correct. P is prime. Now, we have vector space. We have vector spaces over fields. Professor Vero talked about category of vector spaces. So whenever you have a field F, a very standard vector space to look at is F to the N. For example, when we have R as a field, a natural vector space is Rn, for example, R2, R3, etc. Right? Or when we have the field Z2, a good vector space to look at is Z2 to the N. Z2 to the N, for example, Z2 to the power 3. These are vector spaces, right? We've seen this thing before. It's a vectors of element inside that field. For example, Z2 squared means we have vectors with 3 components. All of them are coming from Z2. So for example, these numbers only are 0, 1, 1, 0, 0, 1. These kind of things, right? They all come from the field. Now, if I take something which is a field, which is a ring, but not a field, for example, like Z4, which is a ring, but not a field, I still can consider the same thing. I can consider Z4 to the N. For example, again, Z4 to the power 3. And the elements, there are vectors, they look like vectors, but each component comes from Z4. For example, it can be 0, 1, 2, 3, 2, 3, for example, again, 2. Things of that sort. Now, this is not a vector space anymore because it's not made over a field, it's made over a ring. So if you have a field F, F to the N, a field F to the N is called a vector space. But if you have a ring R, which is not a field, like Z4, you can still look at R to the N. By R, I don't mean real numbers. R is a set here, is a ring, for example, Z4. You can look at Z4 to the N, for example. Does anyone know what is the name of that structure? It's not called vector space anymore because it's not over a field, but it's over a ring. Has anyone heard the name of that? I'm curious to know. Yes, this is called module or module or module. Now, why did I talk about all these things? The reason is that what we just proved, that if AV, yeah, this is left R module in this case. You're perfectly right. I didn't want to get into those things. Now, why did I mention these things? So we saw for a vector space, if A times V is 0, where A is something in the field and V is a vector, that implies either A is 0 in the field or V is 0 as a vector. That is not correct for rings and modules. So for example, take Z4 as a ring, and then take Z4 to the power 3 as module. It is very similar to a vector space. The elements here are things like vectors with 3 components. So Z4 is 0, 1, 2, 3. For example, consider this element 2, 2, 2. This is something in Z4 cubed. This element is non-zero. It has 2 in each component. This element in the ring is also non-zero. 2 is non-zero in the element. So take 2 and multiply that by this thing which looks like a vector, 2, 2, 2. Both of them are non-zero. What is the result of this multiplication? Well, we get 2 times 2, 2 times 2, 2 times 2. But what is 2 times 2? 2 times 2 is 4. Here, we should compute the remainder by after division by 4, we get 0, 0, 0, which is the 0 of that space. So we have 2 non-zero elements. The result of their multiplication is 0. Well, the reason I'm writing down this example is that a lot of you in your homework, or maybe people from 310, the way they've written the answer, they have not really used the properties of a vector space. As you can see, in other algebraic structures, AV might be 0, where A is not 0 and V is not 0. So if you want to prove that for a vector space, you should very in an explicit way use the definition of a vector space. You should say why for vector space is different from the other structures. In other algebraic structures, things like this can happen. Okay, that was the long comment on the first question. Is there any question here? Also, today I think I uploaded the link a little bit late. I thought actually we have the link is set up. I made a mistake. But from next week, I would set up weekly. I would schedule weekly meetings. So it would be good if you don't come late, please. That would be very good. Is there any question here? Okay. So in this course, we do algebra. We do linear algebra. We do linear algebra, but we do linear algebra over vector spaces and fields. Vector spaces and fields. So one could do linear algebra over rings and modules, and that's possible. And that would be another theory anyway. Okay, let's see. What do I want to talk next? Okay, so let's do a little bit simple practice here. The thing is that here, when we had a field, I said we can construct the field to the n, and that's a vector space. That number n, 2, 3, 1, whatever that is, 0, is called the dimension of the vector space. Okay, we can have finite dimensional or infinite dimensional spaces, right? So for example, R2 is, of course, two-dimensional. R3 is three-dimensional. But we have infinite dimensional vector spaces too. So for example, consider the field to be R and consider the space of all polynomials in X. Polynomials in X. Okay. This space is an infinite dimensional space. So for example, something like 1 plus x is here, something like x cubed plus 2x squared minus 7 is here, something like x to the 201 is there, and everything of that sort, okay? This space is infinite dimensional. What does it mean really to be infinite dimensional? And how can you prove something is infinite dimensional? Let's understand that a little more carefully. Okay, so are you familiar with the concept of being linearly independent, vectors being linearly independent?
Yes, we are.
Okay. So yeah, because Professor Viro told me to talk a little bit about dimension and things like that. I just want to make sure we already know. So, well, so you know, we say n vectors we want to Vn are linearly independent if we have this property. If we have any linear combination of these vectors, where these scalars a1 to an, they're coming from the field, if any linear combination is 0, that would imply all of these coefficients are 0. Right? That's called linearly independent. Now, a vector space V is called n-dimensional vector space, or we say the dimension of this vector space is n if one can find a basis for V if there are vectors v1 up to vn, which they are a basis for V, they form a basis for V. That means for any vector u inside V, u can be written as a linear combination of these vectors we want to be. And the second property is that v1 to vn are linearly independent, right? That's called, then we say the space is n-dimensional. So if I want to say, for example, the space of all polynomials, the vector space of all polynomials in X with coefficients where the coefficients are in R, I want to say this is a vector space over R, is a vector space over R. And I want to also say this vector space is infinite dimensional. What does that mean for this space to be infinite dimensional? It means there is no set of n elements in this vector space which they can construct all this vector space, where their span is all of this vector space. So you can't find, so what does that mean is this? It means so there is no number, there is no like natural number n such that one can find polynomials in this vector space, like p1 of x, that's the notation I use for polynomials, to pn of x inside this vector space V, where any other polynomial can be written as their linear combination. This is not possible. Why is that? So doesn't matter how you choose these polynomials. For example, you can take p1 of x to p1. You can take p2 of x to be x. You can take p3 of x to be x squared. You can take anything you want. But if you have finitely many polynomials, you can take, I don't know, x to 2021. Doesn't matter how many polynomials you get, as long as you take finitely many polynomials. If you look at the order of these, if you look at the degree of these polynomials, there is one of them which has the highest degree. For example, let's say here, this is the highest degree. And any linear combination of these polynomials, the degree is at most that degree, right? So if you look at a1 p1 of x plus up to an pn of x, this is a polynomial which its degree is at most 2021. So there is no way you can construct a polynomial like x to the power 2020. You can never construct this polynomial x to the power 2020 using these previous polynomials, right? Now, so there is no way we can choose finitely many elements to construct this space. Such a thing is called, such a space is called infinite dimensional vector space. And there are many infinite dimensional vector spaces. Here, we have a basis. For the interesting thing is that here we have a basis, but the basis has infinitely many elements. So for this space of all polynomials, we can choose this as basis: 1, x, x2, x3, x to the n, and we should continue that to infinity. Any polynomial, of course, can be written as linear combination of these things, right? For example, x 2020 plus x minus 3 is 1 times x 2020, which x 2020 is somewhere here on my list, plus 1 times x, which x is here, plus minus 3 times 1, which 1 again is here on my list. So I can construct this thing as a linear combination of polynomials, but only when there are infinitely many of them. Okay. Now, this is one kind of infinite dimensional vector space. There are even more complicated examples of infinite dimensional vector space. Here, the bases can be counted. The first element of the basis is 1. The second element of the basis is x. The third element of the basis is x squared. The fourth element of the basis is x to the power 3. So there we can count them, right? There are infinitely many of them, but it's not a big infinite. There are infinitely many elements in the basis, but in some sense, it's not a big infinite. So another example we saw earlier in the homework was something like this. Suppose V is the space of all maps from R to R, which they are continuous. This is a vector space. This is a vector space over R. This space again is infinite dimensional. So it's a good question here to ask. If this is, so it's infinite dimensional, you can't, there is no way that you can choose n functions which are continuous from R to R, continuous, such that any other function, such that any other continuous function from R to R, like g, can be written as linear combination of these functions. This is not possible. You can always find another very strange function, which is not linear combination of them. A very good practice is first try to prove this result, this theorem, and then you can think about this. Is it true, like the previous question, that for polynomials, we don't have a finite basis, but we have a basis which has infinitely many elements? Is the same thing true here? Can we present a basis with infinitely many elements such that it's a basis, it constructs all the linear combinations, construct all the functions from R to R? And Yeah, it is related to axiom of choice, but I'm having a more explicit approach in mind here. That is a correct, no, that's a correct thing. And they are linearly independent. And can we explicitly say what are those functions? And can we number them, say this is the first element of the basis, this is the second element of the basis? In another sense, is this question similar to the question of polynomials or not? That's something I would answer next week. I'd like you to think about that a little bit. This is a very interesting question. We can learn a lot from that. Is there any question up to this point? Okay. So let's get to more, maybe a little bit more in the remaining time. Maybe I can solve one more explicit question. So suppose Pn, now I'm defining a new vector space. I define to be Pn to be the set of all polynomials in X over R, which their degree is at most n. So all the polynomials there, the degree is less or equal than n. Now this is a vector space, and this vector space has a basis and has a finite basis, 1, x, x to the n minus 1, x to the n, right? That's a basis for this space. And as you can see, it's an n plus 1 dimensional space. It's a vector space of dimension n plus 1, right? Now, I would, for example, consider P3, the polynomials of degree at least 3, and P4, the space of polynomials with degree at most 4. I define a linear map T from P3 to P4, a linear map, which any polynomial in P3 T would send that to derivative of that polynomial with respect to x minus 2 times x px. For example, if I take, I don't know, x cubed plus x squared, it's something in P3, T of that would be derivative of this polynomial, which is 3x squared plus 2x minus 2x times px, which is x cubed plus x squared, which is equal to, sorry, there's also x here, which is equal to minus 2x to the 4 minus 2x cubed plus 3x squared plus 2x. And as you can see, this is a polynomial with degree at most 4. Okay. Now I want you to, well, let's see. There are two things I want to show here. One is that this map T is linear. This T from these two spaces is linear. Two is that I want, whenever we have two vector spaces, when we set, sorry, I'm going over time a little bit, I think. I would finish, I still have time, right? Yeah, I do have time. One is that I want to show this is, I want you to show this is linear. And two is that whenever you have two vector spaces, you can fix a basis for each of them. So for example, here we have P3 and we have P4. We can set a basis for P3, we can set a basis for P4, and then any linear map, when we set basis for domain and codomain, would have a matrix representation. We can present that linear map with a matrix. So what would be the matrix representation of T with respect to some basis you choose? Okay, think about that for a few minutes and then I would write down the answer. Okay, let's see why T is linear. So the first thing to do is I should show T is linear. So what does it mean to be for a map to be linear? It should respect the addition and multiplication. So if I take two different, well, potentially the same, two polynomials, P1 and P2, I should show it's equal to T of P1 plus T of P2. That's the first thing. So let's see if that's correct. So what is T of P1 plus 2? It's derivative of P1 plus P2 with respect to x minus 2x times P1 plus P2. Well, that's good because we know derivative, taking derivative is linear, right? In general, for example, f plus g prime is equal to f prime plus g prime. That's correct for derivative always. It's a linear operator. So it's equal to derivative of P1 with respect to x plus derivative of P2 with respect to x. On the other hand, 2x times P1 plus P2 is equal to 2x P1 minus 2x P2. Now, I can group these things. I can say I have derivative of P1 with respect to x. I can bring this term next to that. So it would be minus 2x P1. And I can do the same thing for P2. Now, the first part is T of P1, and the second part is T of P2. So T of P1 plus P2 is equal to T of P1 plus T of P2. So first of all, this is the part where a linear operator preserves addition. Now, the second thing is that it should also preserve the scalar multiplication by an element in the field. So if I take a real number and multiply a polynomial by that, this real number might be 2, 5, minus 2, something like that. I should show this is equal to A times T of P. So T of AP is derivative of AP with respect to x minus 2x AP. Well, we know if we have a constant, which A is a constant, it comes out of derivative. So it would be A dp x. On the other hand, this A here is something in the field. It commutes with the variable x and with 2. So it's equal to A times 2xp. So it's equal to A times dpx minus 2xp, which is A times T of P. So it also preserves the multiplication by an element of the field. So T is really a linear map. That much we know. Now, any linear map can be between finite dimensional spaces, can be presented with a matrix. So here T is something from P3 to P4. I should choose some basis for polynomials of degree at most 3, and I should choose a basis for polynomials of degree at most 4. So the best thing I can choose here, the most natural basis comes to mind, is 1x, x squared, x cubed. And the basis I would choose here is 1x, x squared, x cubed, x to the 4. Okay, I should see what is T of each one of them. T of 1 is derivative of 1 with respect to x, which is 0, minus 2x times 1. So it is minus 2 times x, which x is here. What is T of x? T of x is derivative of x with respect to x, which is 1 minus 2x times x, which is x squared. What is T of x squared? It's 2x minus 2x times x squared, which is x cubed. And T of x cubed is 3x squared minus 2x to the 4. So if I want to see what is this matrix, this is how this matrix is made. So here I have 0 times 1, the first element of the basis of the codomain, 0 times 1. And minus 2 times the second element of the basis, plus 0x squared plus 0 x cubed plus 0 x to the 4. So the rest are 0. Look at the second one. I have 1 times 1 plus 0 times x. There is no x, so it's 0 times x, plus minus 2 times x squared. And then there is no x cubed, so there is 0 times x cubed, etc. Look at the third one. It's 0 times 1, because there's no constant, plus 2 times x. There is no x squared, so it's 0 times x squared, minus 2 times x cubed, and there's no x4. And the last one also similar, 0 times 1 plus 0 times x plus 2 times x squared, 0x cubed, minus 2 times x to the 4. So we get a matrix which is 4 by 3. This is the matrix we would get. Now, when we have this, well, there are a few things to see about this matrix. One is that this matrix is 4 by 3. 4 is the dimension. Well, sorry, it's 5 by 4. I'm sorry, because the dimension of the codomain is 5, and then the dimension of the domain is 4. If we choose another basis, so rather than 1x, etc., you could choose, for example, 2, I don't know, x plus 1, x squared minus x, and x cubed plus x squared minus 7. That would have been also a basis. In that basis, and you could choose another basis on P4, you could get another matrix if you change the basis. So this assignment of matrix to a linear map is not something so-called canonical, right? It comes after choosing a basis. But there is a very specific way which this matrix changes when you change the basis. We will talk about that more next week. Is there any question here? Okay, so before finishing the class, I want to say, so I would try that to be the idea of our class. I would try in the first half of the class to kind of spend more time on the homework which you handed in, to reflect a little bit more about that, like the ring theory we had today, that the theorem which you proved for vector spaces does not hold for rings and modules. And then probably talk a little bit about the thing Professor Weir is teaching this week and is related to the homework you would hand in for the next time. Okay, so if there is no question, we can end the class here.